So there's a lot of hype about dancing robots, and you see all these acrobatics happening, and they're doing kung fu dances and everything, and you see robots moving already super crazy. Does this mean humanoid robotics is already AI evolved or not? And this is the topic we're trying to cover today as well, because we're talking about physical AI, especially, and we're talking about to that with Clemens from RobCo, who is the principal engineer at RobCo. And I can only say, welcome back to the RobCo podcast. Hi, Clemens. How are you doing? Physical AI has been all over my newsfeed since I started researching it more and more. And I've come to see that this is such a huge upcoming economy. It's really amazing. And I really wanted to talk about the future of industrial robots, because that is basically, what you're working on. And maybe let's dive into the first topic. And where's the market standing on physical AI right now?
I think there's a ton of developments happening, lots of investments. The promise still has to get delivered.
Yeah, absolutely. But it feels like, and obviously I'm super deep into AI stuff, right? I love how AI is developing and has changed my life over the past 3 years. But I never saw that physical AI, and especially like autonomy of robots, is being seen as a much larger market. And I was always, I understood that robots are going to be a big thing, right? And that automation was always a big thing, but I didn't understand that physical AI is and I don't know how you would put it, but the next level after, us using large language models. How do you see that?
So large language models, if you talk with them and you ask them questions about geometry, then it knows quite a few things, because in order to answer a question with text, you need to understand, for example, where is a city A compared to a city B. So you can ask it things like, it's where is it? Is it to the west or the north?
Mm-hmm.
And this is the starting point of what you could call a world model.
Yeah.
In the literal sense that it somehow knows how the different pieces of the world fit together.
Mm-hmm.
And then, but it's like you cannot ask it, can you grab that cup?
True.
And then you give it to a robot and it would grab that cup.
Yeah.
Because there's so much more to it. And I think the success of large language models has just created this energy to say, hey, now if we can solve language, could we also solve all these problems in the physical world?
Yeah, makes sense. I heard this really interesting comparison. So in large language models, it's all about the data, and the internet obviously being the available data for the large language model. But in physical AI, it's not about data that you can collect in that instant, because it's the collection of photons. That was the thing that I heard. And I found it really interesting, because obviously, like, data on the internet, yeah, you can use a crawler and collect that, but photons are much more information. And I think that's also one of the huge challenges, to collect the surroundings around you in physical AI and then understand it to be able to act upon it.
Yeah, so it's photons, it's electrons, it's protons.
It's way more, yeah.
It's basically, I mean, imagine babies, how they develop in their first year.
Mm-hmm.
Starting, recognizing faces, but then at the end of the first year, they are experts in the physical world, and they maybe have 1,000 waking hours in that time, and so apparently the brain is able to completely get around in the physical world. And basically, what we're trying to understand is, how can we make a machine do these kind of things?
Mm-hmm.
As an example, a 3 months old, if you show it a video of coyote in Roadrunner, and the coyote runs over the canyon, and so runs, and there's nothing underneath.
Yeah.
For the baby would be perfectly normal, but a year later, you would start laughing, because it has learned that it's very unusual.
Yeah.
And so these kind of predictions about the physical world is what you learn during the first year.
Very interesting. What exactly is physical AI for RobCo right now? Because obviously we don't want to talk only about cars and robots and everything. We want to talk about the specific application what you're really working on.
Yeah. So, I mean, we're obviously working on manipulating the real world, right? A robot arm, the main purpose is you wanna change something. So we're not working on running through the world, which is an interesting problem to solve, but it's something where, from our view or the view from our customers, it's not really the most important thing to solve. So for us, it is important to go from, hey, we're programming a robot, and it just is very accurate in going to point A and then to point B, towards having it very reactive to the environment, to have sensors in there so that it can understand its surroundings, and to be able to teach it very, very easily to do certain things, either by showing it something or by moving things around while it's recording something or by correcting it. And so by having this feedback loop, and we're feeding the brain, if you will, to learn these kind of things.
Give me a little bit more insight into why this is so powerful, because I think the thing you just said feels a little bit normal to us because we're using these chat interfaces already, which are giving us great answers. But maybe give us an explanation of how it was 5 years ago and how it is now, and why this programming, this type of teaching, is actually such an incredible advancement and so beneficial for the users.
Well, I mean, we have been automating for over 100 years, right? And so we've reached a point where most of the things that you can program have been automated.
Yep.
You can turn processes into very regularized processes, and then you can automate a little bit more. But now we're at a point where we need to be able to deal with these slightly unstructured environments or semi-structured environments. And then you get to a point where programming these things is just too complex. The amount of code that you would have to use explodes because you have all these boundary conditions and so on. And so then you have to move towards what is usually called data-driven approaches.
Very interesting. Because for me, I always think about, okay, then they build a big factory and they just, they automate the process and then they program it and that works. But obviously, like even the feedback loop to integrate smaller changes to improve maybe the process, the automation process, is obviously much easier when you can teach the machine a new step or even an advancement. And I think that is something that is incredibly valuable, because you don't need to call the guy who maybe initially installed the machine, but you can teach it. And obviously there is also expert level needed to this, but it's much, much easier and much more intuitive, I think. And that's the big thing than it was before. And you can do totally different workflows than before.
Yeah, so I mean, we have this North Star that you should be able to just talk to the robot or show it to it once what you want to do, and just does it. We're not there yet. We've started as a company to say, hey, we want to make things simpler than others, but it still requires quite a bit of expert knowledge, even to do it with UI and without coding and so on. So we want to make it simpler and simpler to do these kind of tasks, and that's what AI will enable us to do.
Of course. Where are we today? Which level are we sitting at? Like, what is possible today, and what's realistically the next level?
So I mean, last year when we thought about how should we structure our work, we thought about, in the end, 5 levels of autonomy.
Okay.
So the 5th level I already talked about. So that's the North Star. So how do we get there? And where have we been? So for us, level 1 is still relatively classic robotics, where you have an algorithmic approach for being able to say, I want to move to point A, there might be an obstacle in, and I have an algorithm, an optimization problem, how to move there. And so what we do there is take the parts of the environment that we're interested in, for example, the robot itself, or certain things that could be in the way, and model that as a digital twin. Also with some physics, be able to write a robot controller requires a lot of understanding of the robot's physics. So that's level 1, very useful. Level 2 would be, okay, so now I'm taking in information. I have a vision system for being able to recognize certain things in the environment. And so with that, that's obviously the first learning-based approach. You can say, okay, I want to identify certain objects, and then I want to parameterize the planner to move in there. So these are things that are pretty established. We have products around it. It's in production in many customer sites, and it's very reliable. Now, what's the next step? The next step is a bit bigger. Now you don't need to take just a single photo, but you have a whole feedback loop running. So imagine maybe a couple of sensors, maybe a couple of cameras. You know where the robot is all the time, and now you can do something which we call imitation learning, for example, which means that you have a means to show the robot what to do, and there are different means for that. And then you feed it through a training process, and it can imitate what you do, but not like in an algorithmic rule-based sense, but it can generalize to a certain extent and can repeat these things. And if we put that into otherwise a flow of instructions that you would still set up in the traditional way, then you get what we call level 3. So level 3 is just embedded feedback loop, learning-based movements and tasks that are part of a larger context. And then level 4 would be that now you take all these program pieces out. So everything is completely learned and maybe imitated, maybe tuned on the side with things like reinforcement learning. But it covers a complex workflow, and I don't have to program anything at all. And I think this is all of these steps we set up so that we don't have to solve this, complete AI problem. We can extract value for every step along the way, and it blends seamlessly into each other.
Yeah, that's so interesting. Do you already know like when these levels will be available for customers, or how long it will take? Because obviously, like when we look at the automation, then some things like the North Star is is pretty far still away. Not inevitable, but like it will take a little bit longer. Whereas level 1 or level 2 are already in action, and then like when is like level 3 already in experimentation mode?
Well, we're experimenting with it right now. Level 3 and level 4, I mean, they're variants of the same topic. So we've built the necessary tools. They are currently expert tools. We're currently looking at pilot customers to try these things out and do feasibility studies and get something out, towards the end of the year. And then there is the interesting question of, when would we get like full level 4? And I think the whole industry makes bets on when this will happen. And we're making our bets. It could be pretty sudden. There could be a pretty sudden jump in success, like task success rates. Yeah. And suddenly it's all over the place, like it was with ChatGPT.
True.
So we're taking our path there. We think that by having software and hardware development combined, and also have a very clear target that we're trying to address. We're in our good state, and others making other bets.
Amazing, I love it. What are the challenges when you're building like these physical AI robots, especially, and what are your biggest challenges there?
So you can't just write a specification and program it and then it works and you do a little bit of debugging. It's more like you have 3 components: hardware, software, and data. And in some sense, these models are just representations of the data that you collect. Yeah. So you need to collect data in a smart way. You need to collect more data than you would previously have to. And so navigating this whole field is what we're trying to do as good as possible. And obviously, you need a lot of domain knowledge in the field and be able to take in all the current research that is still presented at conference and stuff like that.
I think something that you just mentioned is really interesting. So you said it's about the robotics, it's about the programming, and it's about the data. And I think RobCo has a very unique approach to this because you have everything owned by RobCo itself. So the ownership is an end-to-end process. So you don't, produce the machine and then sell it off to someone, but you really you build the machine, you build the software, you collect the data, and you install it also at the client's facility where it's being used. And then obviously the feedback loop is much tighter. But this is also obviously a challenge, but also something that's really special. And how do you keep the full ownership of this innovation, by owning all the production and robot parts in-house? How do you manage all that? Because that's obviously, especially while you're growing so fast, not an easy task, I guess.
I think it's just in the DNA of RobCo. Even shortly after the start, our founders went to their first customer sites and iterated very quickly. And I think for us, it's more like an information processing system. So you need to understand the requirements really deeply. And if you just look at it from the outside, you have, in certain areas, you just have no idea how the real world works.
True.
And so being able to go in, but then also to adapt, I think that requires the full loop. Otherwise, you're just missing out on something all the time.
Yeah, everything's lost in communication, right? It's like this the game kids used to play where it's called like silent. I don't even know what the exact word is, but where you whisper something into somebody else's ear and the message changes along the way. And I think this is a huge problem with when you're not fully integrated. But with RobCo, obviously that is not a problem, but more an advantage. So you can get all that data in and use it straight away. How does physical AI really reduce the time for the robot setup to productive deployment? Because we talked already around the certain levels, but when you're looking at it right now, how does physical AI really reduce the time to deployment when using RobCo machines?
I mean, when we talk about the autonomy part, we're already seeing that you can be much more flexible. People can just upload, for example, a model of the piece that they want to pick, and it gets all processed automatically, deployed automatically, and so on. So in that sense, we're enabling already on level 2 a customer to do things without having to call somebody in. Now with level 3, I think this is still something that we're experimenting with, but we're targeting the same thing, right? Right now, obviously, we're still looking at all the different knobs and so on, but in the end, what you will do is you set up your system. You take, for example, a teaching device, which looks very similar to a gripper, and then you do the task that you want to do n times. And this number might be today a couple of hundred times. It will go down over time. And then the big machine starts to rattle, and in the end you can start trying out the robot, and then as a next step you can watch the robot how it does things and chime in. So you basically take over the control when it does something wrong, and then you can correct its mistakes.
That's very cool.
Right, so this is what we're currently actively working on, and where we see progress over time.
How important in this phase is also like the software architecture? Because compared to obviously the mechanical parts, which are super important to have the arm move the right way or the mechanics really move, but how important is the software?
Well, I think it turns a robot from something that executes commands very efficiently to a data processing system where you have a lot of data intake as well.
Yeah.
And then funneling it such that it benefits the task that you have to do. So, just as an example, if you have 3 cameras, the amount of data generated per second is about 100 megabytes.
Crazy.
So, I mean, you need to compress, you need to manage all of that, and then you need to make sense of that.
Yeah.
So that's now the new challenge or the new task that the robot system has to be able to deal with.
Yeah, makes sense. When you're looking at the modular robot setup, why is that such a vital? Why does that play such a vital role in physical AI, and why is it much better suited for physical AI than like classical or traditional fixed automation systems?
So I think we're moving to a world where the closer the robot becomes to a human, you only have advantages. So, for example, we're currently thinking of a bimanual system, and so now, and the reason is simply because it's easier to learn from humans when you are closer to the human shape. We don't have to solve running around. but you can do it. Now, what if you don't need two hands? You can just deploy a one-armed robot. What if you need slightly longer or shorter hands because the task itself makes it necessary to do adaptations for space reasons, for example? We can easily do that. So I think that sets RobCo apart. It's also parts are serviceable, becomes more maintainable. You can replace something when in the case of when something breaks. And so in the end, we think that for industrial manufacturing, this is a great starting position to be in.
Okay, so looking at how everything has evolved and for me, it feels like that physical AI and AI basically came out of nowhere and then just, was there and changed everything. But for you being in the space for much, much longer, how do you see it? Is it like an evolution of industry production automation, or is it also like a big jump that physical AI has done?
It is definitely a big jump. There were some approaches before in autonomous driving under the label of end-to-end learning. Autonomous driving is in some sense a bit simpler because you can always learn from drivers. So if you have a modern car today, it's a big data collection machine, and then there's the steering wheel and the gas and the brake are the feedback mechanisms. Yep. In robotics, it wasn't quite clear how to do that. But then the big explosion came after ChatGPT and the other LLMs came about, where it said, hey, wait a minute, we could use a very similar mechanism for robotics as well. And then this way make this big leap in AI in robotics.
Yep.
So it was like 2-3 years ago.
Yeah, interesting, because sometimes, for somebody in the industry, it feels different from outside, because you only see like the result, but then it's very interesting that it feels similar for you. When you were looking at the use cases around physical AI, do you have any use cases that you're already serving today?
So we're currently working on concrete customer problems where things are dull tasks, but where like a traditional approach would be too expensive. Very simple things. Imagine you go to a place and buy a bucket of paint. What do you need to do to open the bucket of paint? It's a pretty finicky task.
Yes,
but that's just one example where if you can show it to a robot, then the robot would be able to do it with all the intricacies of wobbling buckets and so on.
That's very impressive. So do you have more examples of how autonomy is already solving problems at your clients?
Autonomy, the big thing is vision. So we have a lot of clients who can, as I said, use their rigid models, so things that they produce in their factory, which can be described using a CAD model and upload it and be able to deploy it right away. Other vision parts are that you can recognize like 2D labels, and you can, for example, boxes from the top, and you can pick it, and we can find the 3D position. And so these are tasks which are already at the state where they have the success rates or the accuracy numbers that our customers need for the everyday work, and where this provides real value.
Interesting that you're talking about accuracy rates, because I have one follow-up question to that. And accuracy for me, when I'm thinking about a production line, is like 100%. But this is not the real life, right? It's always like there is always something. There's always a variance. There's always a margin of error included. How is that handled versus a traditional line compared to one of the more, I would say, advanced lines with physical AI or modular automation?
Yeah, so what is really the important part is how many nines do you have in in your success rates, and you never get to 100%. There's always kind of some issues, and you can either solve it by dealing and tweaking the mechanics. Now we're dealing and tweaking with models. And I mean, we know for certain technologies which are already pretty mature, we can also correct, like we know what kind of mistakes they make. So, for example, if you pick something, maybe you're not accurate in the rotation to the last decimal point, but then you can use a little fixture to correct the rotation. And so suddenly you get much closer to 100%. So these are the kind of things that you learn and that you know when you work in the field on these day-to-day problems. For physical AI, I think we're looking at right now from a base perspective still at lower accuracy rates. And then the question is are there use cases where if you are lower than 99.x% that you already can achieve value?
Mm-hmm.
So, for example, if every 20th time a piece of cloth falls down, you might still create value and there's no damage done.
Yeah.
All you need to do is pick up the cloth every hour or so and put it back into the line, right? And we can still correct in certain times when this kind of thing happens. The second thing is that we're trying to put these feedback mechanisms in so that the model gets better over time, either by direct human feedback or by learning from its own mistakes, so that everything becomes a learning-based system end to end.
That's really interesting because with the code, obviously you can fix something like 100% basically, but you can only fix one very small edge case or case. Whereas with the model, you're fixing for a lot of cases, but then obviously the variance is still there, which is interesting, right? So you cover more by giving it also a little margin of error. It's very, very interesting. Whereas the code has more margin for error because it solves for less problems.
Yes, and also the challenge in the hardware has become slightly different. Previously, we were working on robots that were deaf and blind.
Mm-hmm.
So what do you need to do? You basically need to make sure that you are accurate to the micrometer, getting to a certain position and then being able to do that a million times. Now with the feedback loop, you have different challenges. You might want it to be reactive when you touch something, so then your accuracy goes down a little bit. But you can correct for these errors because you have a camera in, and then you see when you're wrong, so you can correct for it. It's a slightly different problem that we're now trying to solve, but it means that we can solve much more use cases than before.
How do you handle the basically endless imagination you can come up with now for robots and automation and in physical AI that has all the sensors and that basically you can formulate totally new ways of doing things? Like, how do you handle that? Because that is sometimes something where I'm thinking like in an old way, how we thought like the past 10 or 15 years in doing something. And now it feels like endless possibility, right? But how do you handle that? How do you bring that into action? How do you handle your thoughts?
I think we need to be working with a scientific method. Mm-hmm. I think that's it's basically we need to be very careful how we spend our time. So we need to somehow maximize our improvements, the information gain that we get per unit of time. And so we are looking very, very carefully how to set up metrics, how to improve what we're doing over time, how to select the experiments that we run. So otherwise, it's a huge. It's not only our effort. There's a huge community out there of researchers around the world in different labs, industry labs, university labs. Currently, I'm getting bombarded with news every day.
Yeah.
So it is the race is on. I don't know. I don't think that there will be a winner in the sense that whoever comes up with these things first will win everything, like it is in software. I think we can make our point by making sure that we're solving real world use cases and build trust with our customers.
Yeah, very interesting. What do you think there will be like this first moment when factories realize that autonomy has fundamentally changed? Like, did you see that already coming?
I think we will see it when we can empower our customers to do the things themselves that they otherwise would have to get help for.
So you were just talking about the bombardment of news happening, and I'm pretty sure everybody who's working in AI, and especially obviously when you're working in physical AI, the developments are happening so fast that nobody can keep up. And that's why we obviously at RobCo recommend that you keep up with connecting to our newsletter and obviously with the podcast, where we always try to keep you up to date and really go into depth into some of the topics where you get it from, I would say, the principal engineer himself and from the source. And this is our recommendation to keep on top of things, because otherwise you'll be just overwhelmed and you got to really pick your sources. And that's why we want to provide a great source for the industry as well. So thank you, Clemens, for being on the RobCo podcast today and giving us your insights. And I can only ask everyone who's listening, subscribe, join, and come back next time when it's again the RobCo podcast.
Thank you for having me.
Thank you.